let's talk about the basics of HTTP and of the often overlooked and underappreciated protocol stack that it's built on top of that most people call the TCP/IP protocol stack. And this will be on the quiz. It stands for Transmission Control Protocol Internet Protocol. And I'm kidding, of course, it won't be on the quiz, but I think it's worth spelling out the acronyms at least one time. So what is the deal with TCP/IP and what sort of makes it distinctive and important? Let's start with the basics. The version of the internet protocol that is pretty much still most widely deployed is IP version 4. You might ask about versions 1 through 3. Don't ask about them. And you might be like, oh, I've heard IPv6 is now a thing. And yes, IPv6 has been a thing for a long time, but my guess is you're all on an IPv4 network right now. It identifies, an address identifies a physical network interface. In other words, some piece of hardware on some computer somewhere that can receive traffic using 4 octets, which is just a fancy word for an 8-bit byte. Why is it called an octet? Because bytes were not always 8 bits, but that's another story for another Computer History Minute. There's always a special address, 127.0.0.1. That address always means the computer you're typing on. And there's an alias for it that almost universally is localhost. That address, in some sense, exists even if your computer is not connected to the rest of the internet. So if your computer is internet capable, the 127.0.0.1 address is always present. You're always on a network that contains at least one computer, which is yours, localhost. So what about TCP/IP? Basically, it's one protocol stacked on top of another, and this is the way that a lot of network protocols are designed. They're designed in logical layers. The lower layers have to do with how do you physically get information over the communication medium, whether it's a wire or whether it's over the air or whether it's a tin can with a string attached to it. But the first level that sort of becomes interesting to a software person is the IP or Internet Protocol level. Right? So IP is a best effort protocol that tries to deliver packets from one IP address to another. All you can do at the level of IP is say, here's an IP address, here's a small packet which is constrained in size. Please try your best to get it over there. And IP may or may not succeed in doing that. And if you send multiple packets, they may or may not arrive in order or at all. So there's a layer on top of it, TCP, the Transmission Control Protocol, that essentially tries to make IP reliable. It keeps track of which packets have been sent. It waits for acknowledgments from the other side to make sure that it knows certain packets were received. If packets arrive out of order, they're numbered so they can be reassembled in the right order. So TCP essentially makes IP reliable enough that you can have the illusion as a programmer that you just sort of print out a string and that string magically arrives someplace else, unless the physical connection goes down. TCP also adds the notion of a port, which is a completely abstract notion of you've got multiple apps running on the same machine. They need, each app sort of needs to have its own connection so that they don't get confused. And the connections are just labeled with an integer, a 16-bit integer, subject to a few constraints. So the TCP port doesn't mean like a physical port. TCP port is just a number that essentially identifies a particular application that is listening, in some sense, for TCP requests. So you have this really nice abstraction where you can essentially print a string, the string goes into a pipe, there's somebody listening at the other end of the pipe and they just get that string out. And now if they want to reply, they can push a string back into that same pipe and that string will come out the other side. That is a really nice, simple abstraction. And it's easy to overlook some of the really fine points of the design of TCP/IP that allowed it to be adaptable, that allowed it to evolve. Even though the design of the protocols dates from the 1960s, it is still fundamentally the protocol that the internet uses today. And it speaks to the design of the protocol that it has been able to adapt over generations of such different hardware. Vint Cerf on the left there and Bob Kahn on the right shared the Turing Award in 2004. As we know, that's the highest award that can be given in computer science for their contributions to the fundamental design of TCP/IP. Now, it's easy to forget, all of these protocols in red, this is the diagram from the previous slide, all of these protocols are built on top of TCP/IP. They all begin with the assumption that you can just pop a string in somewhere and the other side can pop a string right back at you. And they build their communication, their rules of engagement on top of that. And for a long time, there were many competing protocol stacks besides TCP/IP, especially the X25 family of protocols. But a thing that made TCP/IP the winner, besides the fact that it had a great design and was adaptable and there was a lot of research around it, actually has to do with UC Berkeley. Berkeley Unix, or BSD for the Berkeley Software Distribution of Unix, was the first open source, essentially royalty-free operating system that included an open source implementation of TCP/IP. So when any university or science lab adopted Berkeley Unix, which many of them did because it was high quality and open source, they essentially were getting TCP/IP for free. And a lot of people think that that was sort of the thing that tipped the balance and really, made TCP/IP win the protocol war. And in fact, even Novell NetWare, which was a proprietary protocol that ran over a proprietary sort of connection protocol developed by Novell, there's now a version of NetWare that runs over TCP/IP, acknowledging the fact that TCP/IP is everywhere. So TCP/IP is just printing strings, getting stuff out. What do we put on top of that? And of course, in the case of the web, that is HTTP. And the fundamental operation of HTTP or sort of data structure that you want to think about is a route. A route is a combination of an HTTP method. GET is the most common, but there's also POST, there's a few others. And a URI, some people call it a URL. The differences are minor. I will probably use URI because that's the canonical term. And initially, there were really very few rules about how you assemble a URI. There are syntactic rules. So for example, a URL, the route has to begin with an HTTP method. In this case, in our example, it's GET. It has to specify which protocol is going to be used. HTTP is obviously a choice, but FTP is a choice. HTTPS is a choice. There are other choices. Then there's got to be a host name. Which host do you want to contact and on which port? There is a default port number assigned for HTTP, but you can always override it. Then there's the path. Here's the thing that you're asking the server to hand you back. How that is interpreted on the server is completely up to the server. But as we'll see, some rules sort of evolved, guidelines for bringing a little bit of order to the chaos of what's in the URI path. Then optionally, if there is a question mark is special. It means what's coming next is one or more parameter values, key value pairs. Again, how these are consumed by the server, whether they're required by a particular server is completely up to the server, but we'll look at a framework that sort of codifies some good practices for this. And finally, there's an optional fragment. This began as a way to sort of have bookmarks in the middle of long HTML pages. And so if you wanted to sort of scroll to a specific place on the page, you could specify a page fragment. Right. So these are really just syntactic rules for how URIs work. The verbs or methods that begin the URI, head, which means don't give me back the content, but just tell me some metadata about it. Tell me how long it is. Tell me what data type it is. Get, which means give me a copy of something. Post, which usually means I'm sending you some data and we're going to do something that has a side effect. I'm going to upload something. I'm going to give you data to overwrite something. So get usually has the semantics of I'm getting a copy of something. Nothing is going to be modified. Post usually has the semantics of we're going to do something that changes the state of the world in some important way. There's also put, which we'll talk about later. And finally, there's a delete method, which means delete the following thing. And when we talk about server-side frameworks like Rails, we'll discuss the semantics of what delete actually means. Here's another example. In this example, again, there's a method. In this case, the method is post. This time, the protocol is HTTPS. So what is the S for? S just means secure. We will talk later about what makes it secure and how that's implemented. But for now, in terms of the sort of semantics of how HTTP works, you can really consider them functionally interchangeable. This time, the request is going to localhost. Recall that localhost always means this computer right here. So localhost is always reachable, even if you're not connected to the network. And this time, there's a port number, 3000. So the expectation is there is some program running on this computer. That program is listening, if you will, on port 3000 for a request to come in. And when that happens, it will post back a reply. And here is a slightly longer path. This one does not have any parameters after the URL. It doesn't have any fragments, so it's a little bit simpler to read. As I said, HTTP versus HTTPS. Semantically, don't worry about the difference, but we'll talk about why the S is important and how it's implemented later. It is generally transparent to you as a developer in most cases. So let's actually do a demo. I'm going to do a real HTTP request. And as we'll see, besides the URI part, the request that goes to the server also includes a handful of headers, metadata that the client is providing about what it is expecting to get as a reply from the server. Let's see if this demo will work. Okay, the first thing I'm going to do is I am going to run a program locally that listens for network connections. And I'm going to listen on port 8000 just to pick a number. Okay, it's waiting. And now I'm going to grab a random browser window. And I'm going to visit localhost /8000. Why localhost? Because the browser is running on this computer that I'm on, and I have a program listening on this same computer that I'm on, and it's on port 8000. And what am I going to ask the server to return? Well, I don't care. I'm just going to say /hello/world. I'm going to provide some random URL path. Okay, what happened over here? Well, we've been listening on port 8000, and look, something arrived. The server or the client said get /hello/world, and the client is informing me that it would prefer something, a reply using HTTP protocol version 1.1. These are headers. Each one of these headers tells the server something about what the client is trying to do, like what kind of computer it's running on, the user agent, so which particular web browser, in case the server cares, because it wants to behave differently for different browsers. Things that the client knows how to decode. So it says, if you send me a gzip, a deflate, or a BR file, I can decompress that. And the native language of my human user is US English. So now what happens? Well, now it's our turn. I'm going to be the server, and I'm going to return the simplest possible thing that is legal in HTTP. I'm going to start with, basically a reply that says all is well, and then that got to be followed by a blank line, and I will send back a very short message. And then I will close the connection. It's hard to see, but it worked. That is the world's simplest web request. It's literally just the client sends over a bunch of strings describing what it's asking for. The server sends back a reply that begins with, I'm acknowledging which protocol version I'm going to use it to, a 3-digit reply code, which is 100% of the information about what happened. 200 means all is good. There's a handful of other reply codes that are very common, but this is the thing that is actually used by the client to determine, did the request succeed? After that, there is often, but not always, an optional human-readable string so that somebody looking at the log files knows what happened. But the human-readable string is not actually used to determine the success or non-success of the request. It's just the 3-digit code. So that's about the world's simplest HTTP request. As you can see, the request is not only the route, right? The method, which in our case was get. And by the way, notice that in our example here, we're showing a route as the HTTP method followed by a complete URI, the protocol, the host, and so forth. But when we actually saw what the server receives, right? The server just received get /hello/world. The server did not see localhost 8000. Why? Because that's how we got to the server in the first place, right? So there's always going to be that difference between, if I'm sort of writing out, hey, this is the request you have to do, you'll see the protocol, the host name, the port, and then the rest of the URI. But if you look at what the server sees, it's not going to see the part about the host name and the port because that's itself. That's how the request got there in the first place. Status codes, I mentioned that the status code 3 digits is really the main way that the client knows what happened. If the status code begins with a 2, it means all is well, and there's a few different variations of all is well. 3 means a redirect. The resource is somewhere else. What you asked for is available, but you instead need to go here to get it because it moved. And then there are error codes that have to do with access, like you're not allowed to do that, and error codes like, oh my gosh, I died. The 500 series of codes is that there's actually like a server crash or something that prevented the server from even answering in a reliable way. What if we do a real HTTP reply? So we can do that. Here's what we're going to do for the HTTP reply. Okay, so now we're going to do the opposite thing. We are going to contact a server, but rather than doing it in a browser and seeing the output rendered as HTML, we'll just see the raw output. Here's the page I'm actually going to use. This is just the homepage for the book, so it's some pretty simple Bootstrap and some other stuff. So what does this look like from the point of view of raw HTTP? Well, we're going to use the awesome curl program. Okay, so here's a bunch of texts that you could pretty much believe me when I tell you that this basic HTML looking stuff corresponds to the content here. So let's see how we got to that point. If we scroll all the way to the beginning of the server's reply, which is here. So one difference from when we did our fake server before, this server is saying, I understand HTTP version 2. which has some optimizations for performance. So I'm going to assume from now on, if you want to use HTTP version 2, I'm down. You don't have to, but I know how to do it. And here's that 3-digit code that says all is well. There's a bunch of other headers that are telling us metadata about the content that's coming back. For example, I'm sending you some HTML. It uses the UTF-8 encoding for all of its characters. And it's this many bytes long. Okay, blank line, content comes. That's it. That's HTTP. It is really, really simple, right? And then the rest of it is literally just the payload. So you would think, okay, well, one thing I can do, let me take out the option to show the headers. Let me get just the content, and I'm going to put that content into a file. And now I should be able to open that file in my browser, and I should be able to see like a copy of this page. Oh, I sort of see a copy of the page. Like the text seems to be mostly there, but obviously it looks quite different. Anybody care to guess what's going on? What did I not do? I didn't load the CSS. So if you remember back when we talked briefly about HTML, we said the way that you specify visual styling is you do a cascading style sheet or CSS, and then you essentially link the style sheet to the web page. Well, if we look at the source of the real web page, so to speak, and make it a little bit bigger, and you look at line 24 here, it says that a style sheet can be found at this partial URL. But wait a minute, there's no host name in this URL. Why does this even work? Because when one web page makes reference to content that's going to be loaded, by default, the same prefix is going to be used, right? If I don't provide a host name and protocol prefix to this href, the assumption is it's the same server that just served this same page. So when I do this from a browser, this assets CSS theme.css is automatically going to get preceded by https://sasbook.info, because that's the prefix that was used to fetch the page in the first place. But when I just fetch the page manually, there's no place from which to fetch it, right? It's not clear where to get it from. Therefore, the style file cannot be loaded, and therefore the best that the browser is able to do is render the actual HTML content, but with zero styling information, which you barely see these days anymore. It's like it being naked or something. So that is our HTTP request and reply demo. And the purpose of that was just to show you that you can always look at what's happening under the hood. Curl, in particular, is an amazing tool. It's like a Swiss Army knife for playing around with HTTP, debugging connections, especially when we start talking about calling out to microservices, which we'll talk about next. Curl is your friend. And the CHIPS programming assignment, the early CHIPS assignment in this chapter, is to help you get familiar with how to use this awesome tool.